Good morning, everyone. We're at lecture 21 today. Okay. As you see, I have a pencil again, so we're back in business with doing things interactively. Um, so let's jump into more things on graphs. I just want to remind you yet again, quiz 5 is during class on Tuesday, April 20th. Someone told me that at one point the modules had the wrong day, although in the syllabus it was correct, and it's correct in all my announcements. I want to make sure the syllabus, the modules are now corrected. It's Tuesday, April 20th, 10:45 to 12:05, submitted by 12:35. There are two different reviews for quiz 5. Remember, quiz 5 covers chapters 5 and 6, and it's on the sections that you had homework on. So if you say, but I didn't have homework on that, then there isn't a quiz question on it. Okay? Tomorrow at 2 o'clock, James is going to run a review session. And Monday at 5:30, Nancy will run a review session. And as always, you use the Zooms for their office hours to get to them. They're turning off the wait list during that time. Yes, Jackson?
So for the quiz, there won't be anything on graphs.
There will not be anything on graphs. Graphs are in chapter 7.
Okay, cool. Thank you.
Yeah, I try not to give you anything that's tight. I know this time it's a little bit different on when it is relative to the material covered, but there will not be anything on graphs on quiz 5. There will be material on graphs in the final. Okay, I try not to give you anything certainly before your homework is due, so you have a chance to ponder it all. Okay. Let's remind ourselves we had tons of terminology earlier in the week. And so we know what a graph is, and a graph without loops or multiple edges is called simple. We're going to have lots of stuff to do with simple graphs today. No multiple edges and no loops, okay? And if a graph is simple, we give a walk just by listing vertices. So we don't need to worry about writing the edge down because there's only one edge between two vertices and there's never a loop at a vertex. And so what is a walk anyway? It's a list in general of alternating vertices and edges where each edge connects two vertices. As I said, when we have a simple graph, we do not have to worry about listing the edges because there's only one. So a list of vertices automatically gives you the edges. The length of the walk is the number of edges, and so that's one less than the number of vertices or nodes in a walk. Okay. A trail has no repeated edges. A path is a walk with no repeated vertices. Okay. A circuit is a closed trail. So a circuit can have repeated vertices. Okay. A trivial circuit is a circuit with one vertex and no edges. Okay. A cycle is a non-trivial closed trail where the only repeated vertex is the first and last one. So if we leave off the last vertex, we have a path, since there are no repeated vertices. And finally, an Eulerian trail or an Eulerian circuit is one that goes through every edge. Now, we didn't have this, and our book doesn't cover it, but I just wanted to tell you there's another very famous kind of trail or circuit, and that's called a Hamilton. And just the way a trail goes through edges, talks about edges being not repeated, and a path talks about vertices not being repeated, there's something called a Hamilton trail or a Hamilton circuit, and that is a walk, I should say, that goes through each vertex of a graph with no repeats. So in the case of our thinking about the bridges of Königsberg, that would be like saying you wanted to go on each landmass once, and you didn't care how many times you went over whichever bridges, okay? We're not going to be tested on that. I just thought it was interesting to know. Okay, an edge is incident with a node if it's the endpoint of an edge. If the endpoint of the edge is the vertex. The degree of a node says how many vertices are incident, and a graph is connected if there's a walk between any pair of distinct nodes. Notice this definition says a walk, because we're going to deal with that, a walks and connectedness, shortly. A graph H is a subgraph of a graph G if all the nodes and edges in the H are also nodes and edges in G. So what that means is that the full graph is a subgraph of itself, clearly, but another subgraph is just one that I remove some edges or I remove some nodes, or both, obviously. A connected component of a graph G is a connected subgraph of H such that no other connected subgraph of G containing H exists. So in the case of where you have a connected graph, the whole graph is the subcomponent. Okay? And a graph is Eulerian if there is a circuit that is an Eulerian trail. Okay, we had a bunch of theorems or propositions during last class, and I'm not going to read them out to you. I just have them here because I like to review everything when I can. So you have it all in one lecture. Okay, now there are no proofs here, but just they were last class. But these are the theorems that we had. It's noticeable that you want to say theorem 7.1.2. The point 1 there means, 7.1 means it's chapter 7, section 1, and point 2 is the theorem or proposition in that section. And it says, a connected graph is Eulerian if and only if every node in G has an even degree. Now remember, a graph that is not connected cannot be Eulerian because you can't make a path, you can't make a trail through every edge that goes from one to the other. You don't have a connected trail. Okay. And in any graph, the number of nodes with an odd degree is even. And a non-Eulerian graph has an Eulerian trail. A, it's connected, and if there are exactly 2 nodes of odd degree. Okay, let's move to the new material here. The new material is starting with what we ended last time, namely a graph is connected if and only if for every pair of different vertices A and B, there's a path in G starting at A and ending at B. Notice the definition of connected said there is a walk between the two. A walk can have repeated vertices. A path cannot. Okay? So this is applicable to graphs with parallel edges and loops as well as simple graphs. So it starts out, we have something that says a graph is connected if and only if for every pair of vertices. So what direction shall we prove first? Okay, so let's take the direction that says if for every pair of different vertices in A and B, there's a path starting and ending at B, at A, starting at A and ending at B. Proof. This is the simple direction first. Okay. Given let me call this phrase P. given P, okay, that given P, okay, path is a walk by definition. So there is a walk between any two given vertices that implies G is connected. Okay, that was the easy direction. Let's see, let's try the harder direction. The other direction says, suppose G is connected. And let X and, excuse me, and Y be any two given vertices. Okay. Then there is a walk W between them. Now let's do an induction proof. That's pretty easy. So let's do one. You have some homework induction problems. Okay, so we're going to let P of N be the predicate if the walk has N edges, then there is a path between them, between the start and end vertex. Okay? So what's our base case? Well, it's a connected graph. So we don't have any vertices that are isolated there. So, okay, so we say P1 is the base case. N equal 1 is the base case. But if there's only one edge between them, then that says then the path, the walk is a path. There are no repeated vertices in between because there's no in between. Okay? So then we say, suppose P of J is true for J equal to 2 up to N minus 1, where N is greater than 1. We have to prove it's true for a path of length N. Okay. If W is a path, we are done. So suppose it isn't a path. So suppose it isn't a path. Suppose it is not a path. Then there is a repeated vertex v sub I equal to v sub j, I less than j. Okay, so all of this, we're just following along logically. So what are we going to do? We're going to make a new walk. And our new walk, where am I going to fit it? We're going to squeeze it in here. Our new walk, we're going to say W prime is equal to X is equal to V0. And then we go all the way up. We say that's up to VI minus 1, VI. And then where do we go? We go VJ plus 1. Since VJ is equal to VI, we can know that there's an edge from VI to VJ plus 1 up to Vn, which is equal to Y. Now that's a walk because we got rid of the loop. Okay? The length of W prime is less than n. Okay? Let's call it, it's equal to, let's say m, which is less than n. And by the induction hypothesis, I can't fit this in. By the induction hypothesis, P sub m is true since m is less than n and has to be greater than or equal to 1. So therefore, W prime is a path, and in a connected graph, there is a path between every two vertices, not just a walk, but a path. Okay, we're going to find that helpful soon. All right, let's move on. I'll try and leave more space. I didn't think it would be that bad. So now let's ask a question. Is it true or not that an open walk is a path is it true that an open walk is a path? Is it true that an open walk is a path? Then it's a trail. Let me say, is it true that when an open walk is a path, then it's a trail? Okay, is it true? Well, let's look at that and see what we can come up with. Suppose there's a walk W from A to B, such that A is equal to V0 and B is equal to Vn, and it's a path, but not a trail. What would that mean? It would mean there are repeated edges in it, if it's a walk and not a trail. Okay, that means there's some repeated edge, say EK equals EJ, with K less than J, which means that the edge VK minus 1 to VK, which is equal to the edge EK, intersect the edge VJ minus 1 VJ is not empty. That means that the vertices that make up the edge would have to be repeated for the edge to be in there, okay, in the walk. But that would say it's not a path because we have repeated vertices. And that can't happen. So therefore, a walk that's a path is also a trail. In some books, a path is defined as an open trail with no repeated vertices. Okay, so by this thing that says that if it's a path, it's a trail. That means trail, you can be a trail with not being a path, but you can't be a path without being a trail. Okay, this is in a simple graph. Let me phrase that. Simple graph. No, not a simple graph, any graph. Okay, now our book doesn't use that definition, but we proved it right here. Okay, so that's our first proof. Now, I want you to observe a couple of things. In the first two proofs that I did, I used two techniques. I used induction and contradiction. Those are two very powerful techniques in proving things about graphs. Induction, contradiction, and sometimes you have to do a proof that involves both. And we're going to go through bunches of proofs today to give you a feeling for this kind of thing. So remember, whenever you have to deal with these proofs, you have to say, can I use induction? Can I use contradiction? Okay, those are your hammers. Okay, those are a lot of your hammers. There are other techniques, but those are biggies. Okay, now in 7.2.2, you start out and say you want a simple connected graph and let A and B be vertices such there's no edge between A and B. Okay, so let's just look at the top graph there. That is simple. There are no multi-edges, there are no loops, and connected. If I add an edge A, B to G, then G prime has a cycle that contains this edge. So I can add any edge. Let me pick a simple one. There, I added an edge. I have a loop, okay? But there's not supposed to be an edge between them. So let me add a different loop. Let me add that one. Now I added an edge between A and I. So we have a loop. We have a loop that goes from A to I to B to A. That was not in the original graph G. Okay, where does this come from? It comes from, this is a direct proof. We don't have to worry about either of the other techniques, because if it's connected, you know that between any two vertices, there's already a path, and a path is a trail. And then if I add an edge between the start and end of the path, I have a loop. So is that loop, it's closed, is it a trail? Well, yeah, because the original was a path, which meant no repeated vertices and no repeated edges. And I added an edge that wasn't in the original, so I certainly didn't repeat an edge. So now it's a closed walk with no repeated edges. So it's a trail. So it's a circuit. Okay, so we got it. It's a cycle. Good. Here's a new one. Now this is the opposite direction. Okay, in a connected graph G and a cycle in the graph, pick any cycle. We're ignoring that for now. When an edge is removed from a cycle in the graph, the result is a graph that's still connected. Okay, how would you go about proving that? I told you that we had two hammers, but here's our third hammer. It's a direct proof. How would you go about proving that? Well, you look at the definition. We have a cycle in the graph. Pick any cycle here. Here's one edge, two edge, three edge, four edge. Let me pick a big cycle. There's a cycle. No repeat edges. The only repeat vertex is the beginning and end. That's a nice cycle. Okay. So what are we doing there? If we take out any edge, we say it's still connected. Tell me why it will still be connected. Yes, we have X and Y be vertices and G prime and show they're connected. You're right. So suppose we have a cycle here. I don't want to use those letters because I have trouble, but say I have A is equal to V0, dot, 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 up to Vn, which is also equal to A. Okay? Pick any two vertices in that cycle. So suppose I pick a Vi and Vj such that I is less than j. So what I have is a loop that starts out V0 and it go no direction here. Forget what I wrote here. We go from there to there. I'm going to write dot, dot, dot here. And we have Vi, dot, 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 Vj. And then we go up to Vj plus 1. Vn minus 1. V0, that's Vn. So that's our loop. Now you're going to take out an edge. No, we're removing a cycle between it, so forget that. So j is equal to I plus 1 here. That's an edge. And we're going to take that edge out. Okay? We're taking the edge out, but not the vertices. So can I still get between Vi and Vi plus 1? Yeah, I go Vi minus 1 down to V1, V0, Vn minus 1, Vn minus 2, down to Vi plus 1. Okay, so instead of going from here to here along the cycle, we're going to go all the way around that direction. Okay, now pick any other cycle. We just showed that if this cycle contains the edge Vi plus 1, and we remove it, we can still get from Vi to Vi plus 1. Okay. If it doesn't contain Vi and Vi plus 1, it's still a cycle. We haven't removed anything from it. So clearly we can get to any 2 points there. So it is connected. That's the basic idea in the proof. Okay. Now we get to the things that computer science loves. Lots of algorithms depend on this kind of thing. A tree is a connected, simple graph that has no cycles. Vertices of degree 1 in the tree are called the leaves of the tree. If G is a simple connected graph, a subgraph T is called a spanning tree of G if, first, it's a tree and it touches every node in G is a node in T. Okay, it's a spanning tree. It's a tree. Now, obviously, it has to be connected, and we want simple because multigraphs they have loops, and it's too hard to deal with on something like this. Okay, so a spanning tree of G is a subgraph that is a tree, and it touches every node in G. Okay, now remember, what's a tree? A tree is a connected, simple graph that has no cycles. Okay. A weighted graph, we already talked about this a bit, is a graph that has your standard vertices and edges, and it has a function called W, the weight function or the cost function, that associates a numerical value with every edge. if G is a weighted graph, then T is a minimal spanning tree of G. That means the lowest cost spanning tree. If first it's got to be a spanning tree and no other spanning tree of G has smaller weight. Now, remember, there can be more than one minimal spanning tree. Okay, they're not unique in general. Now, when you have an directed graph with no weights attached, then it's like having equal weights, and any spanning tree is minimal because they're all the same cost. Okay? Okay. Given the tree at the right, pick either one. Let's do the top one first. How many nodes does it have? Okay. So how many nodes does it have? That means what is V in this top tree? It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I get 11. Do you get 11? Yes, Grant.
I just have a question about a spanning tree.
Yeah.
So does that basically mean that every, like, the spanning tree contains all of the nodes from, I guess, the parent tree or whatever?
The parent graph. Yep.
Okay, but it's just,
But it's a tree.
oh, I see. Okay.
Okay. Remember, graphs can have loops. So a tree is its own spanning tree.
Okay, yeah, that makes sense. Thanks.
Okay. But a graph can have loops, not loops, can have cycles and circuits. No loops in a simple graph. Okay, so the number of vertices is 11. How many edges do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 edges. How many leaves are there? How many leaves are there in the top tree? What's a leaf? A leaf, remember, has only one edge emanating from it. The man says 1, 2, 3, 4, 5, and he's right. So the top graph has 5 leaves. If I remove an edge, is the resulting graph a tree? Suppose I remove this edge. Is the resulting graph a tree? Is it connected?
Yeah.
I'm sorry, I didn't hear that.
No, I just said no.
You're right. It is not connected. It's not connected. I'd have a subgraph consisting of these two pieces. What if instead of removing that graph, that edge, what if I removed that edge? Not the node, the edge. So now we're removing that edge. What do we have then? We still have a disconnected graph. I have a tree consisting of one vertex and no edges. And I have another tree consisting of all the remaining vertices and all of the edges except the one I removed. Okay. So it still holds if you take away, you leave a poor little leaf out there on its own. Okay, let's look down here. What do we have? What we have down here is something that's called a binary tree. We can talk about that a little bit later. Why is it called a binary tree? So what are you asking me is yes. I don't know what you're asking about. Yes or no? I don't know what the question is. Tell me what question. What did I ask last? Let's see. Are they still trees? It is not a single tree. The current graph is disconnected with two components that are trees. It is not a single tree because it's no longer connected. If I choose any two nodes and add an edge connecting them, well, I can't do that one. I take it back. Any two nodes that are not connected yet, I can pick these two. Then I still have, it's still disconnected. And the left component is no longer a tree because it has a cycle. Christopher.
So am I seeing that right? Are there two nodes in that first tree labeled A?
Oh, that's always possible. Where would you say that? Yes, there are. I don't mean that.
Okay, thank you.
What that means is that I was cutting and pasting and forgot to give it a different label. Sorry.
No problem, thanks.
All right. So if you add an edge, if you add the edge you took out, if you add this edge, then it's a tree and it's connected. But if you add any other edge, well, if you add an edge between the part you disconnected, like if I add an edge from here to here, then it's a tree again. Okay, because it's connected and there are no loops. So the phrase any edge or something like that, you have to be very careful of how you phrase things. It's not any edge, okay? All right. So the graph is not always a tree if you add an edge, any edge. Now, if I start with a graph and I haven't disconnected it and I add an edge, oh, suppose in this tree I add an edge there. Is it a tree any longer? No. Why isn't it a tree? Because I have a loop. I go from B to D to whatever that thing is, around to K and up here. I have a loop. Okay. So it's not a tree. It's still connected, but it has a loop. So if you add any edge, keeping it simple, you must keep it simple. So if I take two vertices, nodes that are not connected by an edge, not connected by a path of length 1, and I add the edge between them, I have added a loop. We're going to have a theorem on that in a little bit. Okay. So here's a proof. Here's the theorem. If G is a tree and I remove any edge from G, then I get a disconnected graph. Someone asked, is there anywhere you could add an edge and have it result in a tree? If you start with a tree and you add an edge and keep it simple, that means you don't add a multiple edge so that you have to add it between two vertices. The answer is no, you always create a cycle and it's no longer a tree. So if you add an edge between two existing nodes that don't have an edge between them, you've created a cycle if you start with a tree. Okay, I'm going to come back and prove some of these things, but I want to walk on and do some examples of the algorithms we have towards the end of this. I want to make sure we do this. I don't think this one is actually proved in the book. So let's walk around the proof of this and see what we can get out of this. Okay. So what would a phrasing of a contrapositive be? Remember, we have contrapositive, contradiction, and induction as well, direct, but those are main tools. Okay. If G is a tree, then removing any edge. This is the statement. So what do we have? We have removing if removing any edge from a simple graph connected graph G is still connected, then G is not a tree. Okay? So what do we say? We say, suppose we remove, this is removing any edge. If, let me phrase it better. If there exists an edge AB such that if we remove it from the graph, it only has to have one edge, it's still connected, then the original graph wasn't a tree. We don't have to be able to remove any edge, just if there's one edge, that disqualifies it from being a tree. Okay. From G. And G prime is still connected. Okay, that means then there exists a path from A to B in G prime. Okay, so let's call that path, there exists a path W, where W is equal to A equal to, let's say, V0, Vk equal to B. Okay, then let's say W bar equal to A to B0, Vk equal to B. A is a cycle in G, the original graph. I add it back in. So if so, G cannot be a tree because it has a cycle. Okay, so our contradiction says if there's any edge such that when we remove it, we still have a connected graph, then I can look at that path from those two vertices and say, well, add this edge back in. Oops, it's a cycle, so the original graph cannot be connected, cannot be a tree. Let's take 5 and you can ask any questions. Okay? Take your break.
This is just a small question, but is W bar, like, what's the difference between W bar and like W prime?
Oh, It's just whatever notation you want to use. People tend to say, if I'm creating the graph W, I would create a graph, a path W prime. So what I should have done and didn't, it's what happens when I do it on the fly, is I should have called this path W prime because it's in G prime, and then created the path W, which is a cycle. So you just tend to try and keep the same notation. Okay. The bar doesn't mean anything. The prime doesn't mean anything. You could have called it, instead of calling the graph that you create by removing the edge G prime, you could have called it Q or H. It doesn't matter. It's just easier to understand if you keep the notation similar. Okay.
All right, thanks.
Could you also explain just that equals notation for how
Is
you-
someone asking a question or just chatting?
Can you hear me? Hello?
Not very well. And I know my speaker is loud enough because I heard Grant really well. So can whoever it is speak up?
Can you hear me now?
Yes.
Okay. Could you also explain that equals notation that you use to like represent the path?
Oh, that is not standard notation. People write equals, people write colon. I don't know what is the standard notation. I've seen lots of different notation in lots of different books. I have a problem because when I write that, I'm writing those vertices are the same, but A is not the path. So you have to be really careful, and you can't really write parentheses because that's an ordered pair, and you can't really write. So we have an overload here on notation. Okay.
Okay, but you're basically saying that like A is the same vertex as V naught.
Yes,
that-
that's what I'm saying. I'm
And
saying
then-
when you're starting that path, I'm calling it V0 as part of the walk, but I'm starting it at A and I'm ending it at B. And I'm saying that I end up by using the notation V, then I know how many elements are in the walk. Okay.
Okay. Yep, that makes sense. Thank
It's
you.
only to help us know how many elements, how many vertices, how many edges are in the walk. That's all.
Okay.
I hope you all like that winter has come back to Salt Lake. I don't know if you're all here in Salt Lake, but it's winter here. Yeah, I wonder what flowers we'll get this May too. Gosh, I hope we don't get dead ones. It's snowing, but it's really not that bitter cold. So I hope all the blossoms don't freeze because we need the fruit on the trees. Oh. Okay, now I'm back. Here in example problem 4, we just looked at that and saw what happens. And the proof basically follows that reasoning. So it's in your, I believe it's in your slides already. Okay, so if you have a tree and you take any edge away, it results in a disconnected graph, typically with 2 connected components that are trees, because there's no cycles in either component, okay? And it's a proof by contrapositive. Okay, let's look at proposition 7.2.4. For every connected graph G with at least one edge, if G has no cycles, then G has at least one vertex of degree 1. What's the contrapositive statement to that? What's the contrapositive to that? Take a stab. Volunteer somebody? You can say it out loud. I hear you now.
Could it be a graph with, or if a graph with node G has a degree of 0, the graph can't be connected?
Sorry. Well, maybe. So what I would tend to say is this all is known. So we have to start with that. And then this is P and this is Q, right? So it's connected. Okay, so we can't have a vertex out by itself with no edges. Okay, so what we're saying is not Q means G, the degree of all nodes in G greater than or equal to 2. So if the degree of all the nodes in G are greater than or equal to 2, remember it's connected, so it can't have any node with degree 0. And if we're saying the contradiction that it doesn't have any nodes of degree 1, then we're saying that all the nodes in G have to have degree greater than or equal to 2. Then what's the contradiction of G having no cycle? Then G has at least one cycle. At least one edge. Yes, your statement here in chat is correct, but I think it's a little harder to understand. Because if we say that the degree, it's the same since it's a connected graph, but if we say that the degree has to be greater than or equal to 2, the proof of this goes along and says something like the following. Okay, it says, for example, if I pick any vertex to start with, call it V0, and we suppose G has n vertices. Okay, and we pick a vertex and we go out along one of the edges. Remember, it has degree at least 2 here. So we go out on an edge and we pick one of its edges and we go out along the edge. And we find vertex V1. Always start the implication with if. Okay. V1. Now, Can we keep going from V1? Yeah, because V1 has at least 2 edges. So we've only used up at least 2 edges emanating. So we've used up one of them, so we can keep going and go out the other one. And then we get to V2. And then we get to V3. In each case, we're using up one of the edges coming into the vertex and going out on a different one. Okay, and we keep going until we get to edge Vn. Okay, now we can stop there because what we're saying is I have a path, or I have a circuit with at least, walk at least, with at least n plus 1 vertices. I don't have a circuit, I have a walk with at least n plus 1 vertices in a graph that has only n vertices. What does that mean? That means that at least one of them is repeated inside or using the edges. And that means it has a cycle. Okay. Do you understand that? So we've proved the contrapositive. So therefore, we proved that if all the nodes in G have degree greater than or equal to 2, then G has to have a cycle. So that means that all the nodes cannot have degree greater than or equal to 2, but since the graph is connected, that means that at least one vertex has degree 1. Okay. Now we have for every tree with at least 1 edge, G has at least 2 leaves. What do we know? We know that the number of vertices with odd degree is even. Okay, so from proposition 7.2.4, that if G is a connected graph with no cycles, then it has at least 1 vertex of degree 1. And we know a tree is a connected graph, simple, with no cycles. So it has to have at least 1 vertex of degree 1. Now we know that the number of vertices of odd degree in a graph has to be even. So that means it can't just have 1 leaf. It has to have at least 2. And that's basically the proof for this. And I'm not going to write it down now because we're going to move on. I hope everyone sees that. Tell me if you have trouble with it. So that uses the definition of tree plus 7.2.4 proposition plus the thing we proved that the number of nodes in connected graph of odd degree is even. And those all lead to the conclusion. This would not necessarily be an induction proof because you don't need to do that for this. You could, but you don't need to. Okay. Yeah, I guess I did do it induction. Okay. Let's look at this one, and this one we've got right on the page here. In a simple graph, remember that means no multi-edges, no loops, with distinct vertices A and B. If there's a walk from vertex A to vertex B, then there's a path from vertex A to vertex B. What's the predicate for proving this? In a simple graph G with distinct vertices from A to B, if there's a walk of length n from vertex A to vertex B, then there's a path from vertex A to vertex B. So that's our induction proof here. Okay, the base case is pretty easy to prove. Base case is a walk of length 1 between them. There are no walks of length 0 in a simple graph, and the vertices are distinct. Now, remember, in this graph up here on the right, I can't connect a vertex in the top component to a vertex in any of the others. Okay, so it doesn't have to apply to just connected graph. It says if there's a walk between two vertices, then there's a path between two vertices. And the proof here, I want to go through this just to talk with you because some people said they didn't understand how they were using induction in a proof. And so here's a good example of that. So we're going to assume we've already looked at the case, the base case that says if there's a walk of length 1 between two vertices, that means it's a path because there are no repeated vertices. You're done. Okay, so we assume it's true. Pj is true for j goes from 2 to n minus 1. We want to prove it's true for Pn. So we take a pair of different vertices and let W be a path between them of length n edges. Not a walk, I'm sorry, a walk, not a path. If it's a path, we're done. If it's not a path, that means, what does it mean? It means there are repeated edges, repeated vertices. Wow, my brain. Okay, so there's a vertex I that's repeated in the walk. Suppose I is its smallest subscript and j is its largest subscript. Okay, then we create a new walk, W1, that goes from A to V1 to V2 up to VI, because that was there before. And then we go to edge j plus 1, because edge j plus 1 goes from VI, which is the same as VJ, to VJ plus 1. And then we keep going up to EN and then B. Okay? The new walk has a shorter length, less than n. The walk is less than n. We don't know it's a path, we know it's a walk. But we have our induction hypothesis. Our induction hypothesis says if I can connect two edges by a walk of length n plus 1 or less, then there's a path between them. So I've connected A and B by a walk of length n. I started with one of length n. I've now connected it with a walk less than n if it wasn't a path to start with. So therefore, there's a walk between them. And that is the induction proof. Okay. Now, some people said in their proofs, what they did is they said, well, I made a shorter walk. Now I'm going to make a shorter walk again and again and again until there are none left. What you are doing then is basically a hard version of induction. Our induction says we can use the fact that we already know we can do it without saying again and again and again. Okay. So we already know that. So let's look at a tree with n edges. This theorem says if you have a tree with n edges, then it has n plus 1 vertices. Okay, so By induction, every tree with n edges has n plus 1 vertices. A tree with 0 edges has 1 vertex. So P sub 0 is true. Notice in some of these cases with graphs, we start counting with the base case of 0. Okay. Sometimes we use induction on the number of edges. Sometimes we use induction on the number of vertices. Okay. So we assume it's true up to Mary minus 1, and then we look at a tree with Mary edges and take away an edge. From the practice problem that we just walked through, that results in a disconnected graph T prime that has 2 connected components, H1 and H2, each of which is a tree. Why is it a tree? Well, it's a connected simple graph and it has no cycles, each component. Each of those components we already know has K1 edges, say. So it has K1 plus 1 vertices because, why? Because we're invoking those because it has fewer edges. And so we just add up everything and say in the original graph, we have 1 more edge, the same number of vertices in total. So that's where we get n plus 1 in general. Again, induction on the number of edges. In this case, we're relating edges to vertices. Okay. Prove G is a tree if and only if 2 nodes of G are joined by a unique path. Unique path. So we know that if G is a connected simple graph, G is joined by a path. If it's joined by a walk, the definition, everything, any 2 vertices are joined by a walk, they're joined by a path. Now this says that path is unique. There's only 1. How would we prove that? Would we do it by direct proof, contrapositive, contradiction, or induction? I do it by contradiction. Okay. So I say G is a tree, and I've got 2 nodes, at least 2 nodes, A and B, that are joined by 2 different paths. Okay. So I have path 1, which is A, V1, V2, VK, B. And I have path P2, which is A, W1, W2, WQ, B. 2 different paths. Okay. Now I can look, and I can just look at this and say, well, if they're 2 different paths, maybe some of the vertices are the same. So clearly A is the same. It could be that V1 and W1 are the same. It could be that V2 and W2 are the same, but at some point we're going to have some different vertices in that path. Okay. So we're going to suppose that VI is equal to WI, but VI plus 1 is not equal to WI plus 1. That's where they start differing. And then we're going to find the first vertex Vj, which is going to be equal to some WL. That's the first vertex, again, where the vertices in the two paths are the same. Okay? Remember, a contradiction, what we're going for is to say that if the conclusion isn't true, then there's a contradiction in the hypothesis. So now we have something. I'm going to create Wi plus 1 all up to WL. And then we're going to go Vj minus 1, Vj minus 2, all the way back to Vi. And W, that's an L, wasn't it? No, that's Wi plus 1. Yeah, so that's Wi, which is equal to Vi. Okay, this is a loop. Okay, so what we've said is if I can go to there, and if I have something here that's a second loop that goes like that, then it says I can form a loop out of those two paths. Some of the vertices are the same, but some are different. They have to be if they're different paths. So I have a loop, I have a circuit. None of the edges are the same because I said none of the vertices inside it are the same. So I have created a circuit. Okay. That's a cycle, which implies G is not a tree. And that's a contradiction. That's a contradiction. The slides are, the slides should be in the modules in the section where it says class lecture for this week. Okay. I put them there last night, so if they disappeared, it's beyond me. Okay. So let's talk about spanning trees. Oh, this is the most fun, and I'm barely there. If G is a connected simple graph, for each I, as long as there's a cycle in Gi minus 1, we're going to take any edge in the cycle Gi minus 1, form a subgraph of G by deleting E from Gi minus 1 to form Gi. So I'm taking away edges as long as an edge from a cycle. And we have a proposition that says for any simple connected graph, the spanning tree algorithm produces a simple graph. So here we have an example. I have a simple connected graph. Okay. So let's look at the loop. Let me try it in red. I look at the loop B to I. Well, that doesn't make sense. Oh, right. B to I. In this one, I look at B to I to G to H to B. There's the loop. And I'm saying I can pick any edge. So I'm going to pick the edge IH and take it away. So this is the result of that removal. This next graph is the result of that removal. So I take any loop that's left, namely over here, I take the loop A to B, A to B to C to A, and I decided to remove edge AB. There's no rhyme or reason. I'm just picking one because it's complex. And I take away the edge AB. You could have picked a different one and you'll get a different spanning tree. So now I'm going to pick the cycle B to I to J to F to H to G to B. Now look what happened. You know, we originally had in the original graph, we had a smaller cycle because we had the edge from F to H that broke it into 2 cycles, but now that's just one bigger one. So I picked that one and I removed the edge GH. So this next one doesn't have the edge GH. And for visualization purposes, we move G out of the way. We don't move H yet. Okay, the graphs, these 2 graphs are the same. I just moved H. I changed no connections, no edges. Okay, so what does this one say? Choose. What did I choose? I choose J, D, and F. So I choose that loop and I removed the edge JD. Okay, and you see it in this picture here. Again, now we move H out of the way. And we look at the loop. What loop are we looking at? Now we're going to look at the cycle B to C to D to F to J to I to B. And we decided to remove edge BC. You're looking at the graph. You don't need to see a visualization of the graph because this is something that you have to be able to compute loops. That's all you have to be able to do, not loops, cycles. You have to be able to compute cycles in between each of these things to see what's changed. And then we keep going until we finally get here. Is that a tree? Are there any cycles? No. Is it simple? Yes. Is it connected? Yes. It's a tree. It's a spanning tree. At every step in this algorithm, we could have picked a different edge to remove, and we would have gotten probably a different spanning tree. Okay, so spanning trees are not unique. They're not unique in the number of edges. What is the critical thing in a spanning tree? It's a subgraph of the original graph. It's connected, it's simple, and there are no cycles. And you get to it by removing cycles. We saw over here, from here to here, that when we removed one edge, you would have thought I reduced the cycles, but I didn't. I had 2 cycles here and I have a big cycle here. So taking that edge away, I guess it reduced it, but it made a new one. So at each step, the cycles may not be the same cycles that they were in the previous step. Okay. I don't think I have time for Prim's minimal spanning tree, but that's a fun algorithm. We'll start with that next time, and then that will be after your quiz. Your quiz is on Tuesday. Okay, quiz 5, Tuesday. Review sessions tomorrow and Monday. Are there any questions? We'll start with Prim's next Thursday. Let me give you a header. Prim's is great. Okay, I start with the same example, but I put some weights on the vertices, and this is in the slides that I already gave you. And I started it out already. Okay, now Prim's algorithm, if you take some time and try and do it yourself, Prim's algorithm says you're creating something called a minimal spanning tree, remember. And that's because you're taking something that has the lowest cost function. That is frequently not unique either. Okay. So there can be more than one minimal spanning tree. But this thing says if you have minimal spanning tree, this is a nice greedy algorithm for finding, just as we found a spanning tree with a greedy algorithm, we can find a minimal spanning tree with a greedy algorithm as well. And it's kind of cool. We can start anywhere because it's a tree, and we can end up, it's a graph, I'm sorry, but we can find a minimal spanning tree of the graph, connected simple graph. Okay, notice how important the words connected and simple are here. All right, are there any questions? We're going to start with Prim's algorithm next time because I have this beautiful example that I'm doing, and I can't give that up. We have to start with that and go over it. Read over it and try it yourself. Sometimes you have in the algorithm and it says, look at the minimum cost, and then you're picking an edge with the minimum cost each time to put in the tree. And sometimes you have adjacent edges, so to speak, that the lowest cost, more than one edge has the lowest cost, and that's how we can wind up with different minimal spanning trees. Okay, if you can't find the slides, send me a note, and I will double check them, but they were there this morning, I thought.
Are you
Okay.
talking about the pre-lecture slides?
No, I'm talking about this class lecture slides. If you look in this week's modules, whatever week we're in, 13, something like that. If you look at the bottom two sub bullets there, one says class lectures and one says class discussions. And if you click on that, you come to a page that will point you to the slides from this lecture. I've done that the whole semester, so all the slides from class lectures are available. Okay, the bottom two sub bullets in each week's modules, I think they're the bottom two. Okay, and both days worth of slides are there. Okay.
Yeah, I found it. Thanks.
Great. I'm glad. Good. All right. I will see you. Well, I'll be checking in on Tuesday during the quiz. Remember, please, you have to get it uploaded to Gradescope in time, or you have to, if you can't upload for some reason, you have to get it to the TA named on the rules sheet by 12:35 on his email clock, which we don't control. Okay. All right. Good luck. It's on chapters 5 and 6. Do well. Remember, next Thursday is the last new material because the following Tuesday is the last class, and that's review. Someone asked about the homework because I'm covering new material on Thursday and it's due on Friday, and gee whiz, it looks hard. And I said I was contemplating making some changes with respect to the homework so that it was less taxing for you. In that respect, I said I'd try and have a decision by tomorrow afternoon. So please check the announcements. Check the announcements before you wade into homework on sections 3 and 4. Sections 1 and 2 problems will not change, but before you wade into 3 and 4, check for announcements. If there isn't one, there will be one shortly. Okay? Bye. Have a good weekend.